Okay, I will begin. Hello everyone, I'm Wenyu. I will lead a discussion on mineralogical underpinnings and planetary implications of terrestrial and Martian serpentinization. At first, I would like to introduce the author who did all the works, Benjamin Tutolo. He is currently an assistant professor at University of Calgary, and he was also doing his postdoc at University of Oxford. He received his PhD at University of Minnesota and his bachelor at Pennsylvania State University. His what? Sorry. His research include hydrothermal processes, diagenesis, and carbon dioxide. So we may know serpentinization is apparently worth of understanding. And so if we consider only the magnesium and members, the reaction can be written like this. So namely, 2 olivine and 3 water H2O and react and will produce brucite and serpentine. There is also a contemporaneous reaction. The olivine also reacts with silica sourced from adjacent minerals. And this reaction will produce serpentine only, so without brucite. There is also a later stage brucite silicification reaction, which may occur, and this will consume brucite here to with silicon dioxide to produce serpentine and water. Sorry. So from all these equations shown here, we can basically safely draw a conclusion that either silicon dioxide would be quantitatively removed from the solution. So in this case, the brucite would be the excess component, or brucite should be quantitatively converted to serpentine. And in this case is the otherwise, namely the silicon dioxide will be the excess component. And also we can draw this conclusion from this figure. So this figure shows here, so it tells us the brucite can only stably exist when silicon dioxide concentration is low enough, like here. While recent measurements from this lost city hydrothermal field, these measurements show that silicon dioxide can exist in serpentinizing environments. And from these measurements, it suggests in this environment, maybe these hydrothermal fluids are not always equilibrium with their geological surroundings. And because so the people want to explore this more, And also because this equation is tractable. So this equation used in the paper to examine reactive transport processes during this serpentinization process. And here is the result diagram. And so they try to fit the line of the plot in this figure, so this line. And so by doing this, they showed that Brissett silicification is a rate limiting reaction. And this reaction order is 1.5 with respect to aqueous silica. And so they also draw this rate equation here. They by fit the line. And so because this rate law show that like the factor of the constant above in the front, constant in the front is pretty small. So this also demonstrates that both brucite and silicon persistent in serpentinizing environments. So this can like answer the question before why these measurements show that there are elevated levels of silicon dioxide. And they also did another interesting work, and this work was on cobalt hydrogen production in Precambrian serpentinizing systems. And so if we want a more generalized reaction of serpentinization reactions, it shows here. So it's basically an interaction between olivine and seawater, and it will yield some dissolved magnesium ion, and also ferrous ions, and silicon dioxide, and also water. And specifically, if the reaction was under like higher temperatures, namely higher than 200 degrees Celsius, magnetite is what will be produced. And if it happens under lower temperature, and brucite and serpentine, also cobalt hydrogen will be produced. And so here they state the amount of cobalt hydrogen produced is directly proportional to the abundance and oxidation state of ferrine in the serpentine, and also any ferrine which is not participated as a serpentine will be accommodated through a variable ferrous ion component in brucite. So this is the reason why the authors in this paper, they did some experiments to explore the mechanisms of ferric ion substitution in serpentine by using Morse-Bohr spectroscopy. And before having a look at the results, here is a diagram showing two different coordinated ferric ions. So namely the octahedral ferric ion and also tetrahedral ferric ion. And here is their result diagram. Let's first take a look at figure A, and the x-axis here is the ratio of ferric iron and total ferrium, and y-axis here is the ratio of tetrahedral ferric ion. This one, and the total ferric ion. And from this result, they draw two conclusions. The first is that they think the mechanism for ferric ion incorporation in serpentine is independent of the bulk ferric oxidation state. And the second is pretty important for this work. This is so this result also indicates an overall trend of this substitution here. Because so they said in the paper, all but one of the compiled measurements feature extensive tetrahedral ferric ion substitution for silicon. So that means they got this result. The ratio, like the ratio of tetrahedral ferric ion and total ferric ion equals 0.443. That means there are some ferric ions substitute silicon. And here is also some result diagrams. So this shows the relationship between silica deficiency in serpentine and the amount of coupled hydrogen produced during the process. So the yellow means more coupled hydrogen was produced. So it shows here less silicon and more ferric ion will make more coupled hydrogen produced. And for in terms of magnesium is so it's the opposite, like for less silicon and also less magnesium will make more coupled hydrogen. And these two diagrams showing here, they wanted to say if coupled hydrogen is abundant enough in the solution, then the ferrous iron can stably exist. So namely, because the x-axis is the coupled hydrogen concentration, and so the right part of this diagram shows that there are always ferrous ion, and the left part shows ferric ion. So this is the same case. The upper part there are more coupled hydrogen in the upper part of this diagram, and there are ferrous ions in these minerals, And for the lower part, there are more ferric ions in these minerals. And at last, they also did thermodynamic calculations. They used the result to illustrate the silica limitation on coupled hydrogen production. And so it's basically the same as before, less silica dioxide, more, and there will be more coupled hydrogen. And they also compare modern seawater with Precambrian seawater here. And this indicated that more coupled hydrogen will be produced in modern seawater at the same time. At the same temperature, due to more silica deficiency. And that's all. Thank you.
Okay, thank you, Wenyu. So any questions from participants today? Or any question from you, Wenyu, about this paper?
I can't hear you. Is anyone speaking?
I was asking that, do you have any question for this paper?
Okay.
Or what do you think any part that is wrong or unclear in this paper?
I did not understand. This part actually, they stated here the amount of coupled hydrogen produced is directly proportional to the abundance and oxidation state of ferrium. I saw in my, because I didn't read all these papers in the reference list.
So you don't know why they are saying that? Is that what I mean?
And also why they started to explore the mechanisms of ferrium oxidation.
What oxidation?
Ferrous.
Ferrous. Oh, ferric iron. Ferrous iron is the iron 2 plus, and ferric iron is iron 3 plus. The reason that people always link these two together for iron 2 plus and iron 3 plus with hydrogen production is that because for the hydrogen, normally hydrogen stays in the water, so the hydrogen stays as a hydrogen plus. But when the hydrogen becomes a hydrogen gas, then it needs to change its valence state. So that is a redox reaction. So you always need to so for H2O, it basically becomes an oxidized form of hydrogen, H plus, to turn into a reduced form of hydrogen, which is H2. So by that, then you need to oxidize some valence state of elements. And because iron is the most common major element with a variable valence state, so normally that people would link that to the major element, that is iron 2 plus, iron 3 plus. So it's a so that's why people are talking about it. And in this work, they try to make the olivine relatively simple. They're trying to only look at the magnesium and member, as well as iron, I suppose. So yeah, but think about it. For magnesium 2 plus, Mg 2 plus, it is 2 plus in the olivine, and it's also 2 plus in the water, which is aqueous. That's what people are showing here. So whether magnesium stays in the water or stays in the olivine will not produce a hydrogen, because the hydrogen gas have to be reduced from the water. So so always needs to also needs the element to be oxidized. So iron is a proper member for doing that.
Okay.
Actually, this is what is very important reaction that people have been thinking. Let's say Earth science community. I think for different aspects. Probably in your introduction, you have not talk all the parts. Also, including this paper that didn't talk all about it. Is that for hydrogen production? First, that it is very important for the possibly for the generation life. Also what they briefly point out in the paper, but didn't went into more details. And then hydrogen is very important, possibly for people to think about to generate power. For one example is that now humans have the plan to land on Mars in the 2030s or 2040 or 2050s. So for the first group of people who are going to Mars, we won't carry too much energy with us because it's a very long travel, and there's only limited amount of thing that people could carry in terms of the mass by the rocket. So people have been thinking of producing energy on Mars. So this reaction, serpentinization reaction to produce hydrogen, basically is a very possible way that people are thinking of how to produce energy as well as water on Mars in the future once we have humans as astronauts landed on the Mars and then come back, or maybe never come back, but they still need to gather the water there as well as energy. So this is important reaction for that reason. Another very important reason for hydrogen in itself is that people have been debated over many decades on different aspects from the early Earth atmosphere, that why hydrogen could be generated and being lost into the atmosphere, because once hydrogen is very low density, it's very easy to leave the Earth's atmosphere and enter into space. And this hydrogen will dramatically differentiate the hydrogen isotopes that people could measure. And also that's a very effective way of losing hydrogen from the Earth to the planet, and also that will change oxygen fugacity of the Earth's surface, because as I pointed out earlier, so if H2O, then hydrogen is H plus, but once hydrogen is lost into space as H2, then basically that means the rest of the Earth's surface will become more oxidized, because a reaction needs to occur to produce hydrogen gas, where it also needs to oxidize something. And normally it's iron. Is most appropriate, like the most common substitute people have been thinking about that being oxidized. So that's I think that's the importance people have to think of, and also that's the reason why they need to talk about iron when they produce hydrogen. Okay, do you have some other concerns or unclear parts you think the authors need to clarify? Okay, could you move to another page? Actually, I didn't see it very well when you moved along the pages. Could you move to the next slide? Am I stuck, or when you got stuck? Okay, so when you need to exit and then comes back. Okay, when you move on. Okay. Okay, this slide. Let me think about it. So what they did, okay. So my understanding is that, okay, they constantly, they have a time series measurement for the silicon dioxide concentration in water. Is that right, Wenyu? Wenyu, could you hear me? Okay, my understanding for that, okay, actually it was that page, that's fine. Yeah, this one. Wenyu, could you hear me? Okay, I don't know whether Wenyu could hear me or not. So okay, you hear me. So my understanding for this figure is that what they did was that the authors, they measured the silicon dioxide concentration in the water, and they measure it at different time. So they do have a time series of analysis on silicon dioxide or silicon concentrations, and then for each silicon dioxide silicon concentration, then they calculate their activity. So that's that one, I get it. So in different time, and then they also looks at the rate in terms of that. Okay, so what is the rate for? This rate is not the concentration in uptake. What's that? It's meters per second. I didn't fully get that for the rate. How did they measure that? How did they calculate the vertical axis? Yeah, for this one, for the vertical axis, is this not the rate of concentration change? If this concentration change, then that should be the silicon concentration per second. So, and then they measure certain area, right? Okay, then that makes change. Okay, service normalized rate. So they have a certain service that they allow, let's say, I don't know how they confine that. And then this versus happens on the service. Yeah, yeah, yeah. That I can understand. I think the very guys are now understanding that. So they look at the service and then look at how, like say, they measure in different time, and then they look at how silicon that accumulate. So basically by that, and then the horizontal axis is that they measure the water concentration each time, and then they could calculate the activity of silicon dioxide, and then they create this Arrhenius equation. So I think K and A. So how does A and K both come from? Because you know the rate, and then you know the silicon dioxide activity. Then how do you know K and A at the same time? Yeah, how do you know? And N, you have to solve three problems in one, right? Okay, so they do the log. Okay, let me see. They do the log, and then they want to basically mix the K. How do they do that? I think they want to have a y equals ax plus b, something like that. Then they have the slope as the K or A. Is that right? Does it take log on both ends? Log. I forgot. That's.
If you get the I think if you get the log diagram here, and the slope, which means the n, because after the calculation, the n stands for the slope in log diagram, and the constant in the last item here it is 3.39 here stands for the k multiple a. I think it's the combination. It's a product of k and a, which stands for here.
Okay.
Negative.
I see.
Yeah.
I see. Okay, thank you. I think that makes sense. Okay. Okay, that makes sense. Okay, could you turn to several pages later, where they show the Precambrian? Okay, maybe for this one, I could briefly explain. So octahedral basically is octahedral. So 八面体, they have 8 faces. Tetrahedral is basically like an island. So there's a 四面体. So that's different atomic position or the structure of the different silicons. So that's a different position that stand on. And iron 3 plus could either stand in the center of the tetrahedral, or they stand between different tetrahedrals as the octahedral. I think that's how it works in serpentine. And okay, so Wenyu, could you move on to another one? I think in another one. Okay, let me see this one if I understand. Okay, so for this, they try to link the deficiency of the silicon in the serpentine with a ferric iron. Okay. So basically, then the more iron 3 plus you have, then the less silicon you are going to have, because they have that reaction. Have silicon is a 4 plus, and the magnesium 2 plus, and then they replace for iron 3 plus. And okay. Could you move forward? Okay. Could you? Okay. For this one, they have the hydrogen generated per mole serpentine. So hydrogen could produce a lot once silicon is really deficient. That makes sense because they have a lot of iron 3 plus. So being oxidized. Okay, that's expected. So could you move forward? I think for this one, I think this is what they produce in their. Is that what they get in their paper, or this what they cite other people's work for this one?
I think they get it from their own work.
Okay. That looks like very clear. So sometimes I doubt. Sometimes I'm a little dubious about real experiment data. This.
I think they wanted to say that maybe the pH thing they wanted to talk about
pH. Okay, pH in the water.
Yeah, and also so they wanted to say if carbon hydrogen is abundant enough, and then the ferrous ion will be stably existed.
Okay. Okay, so but for here is all ferrous iron, right? So it's
No,
all
this one. Oh,
okay. This is ferric iron. Okay, this one is ferric iron. So
oh,
once
the upper
okay,
lower part, there are some ferric ions in these minerals.
okay, once they have very that's expected. So you have silicon dioxide is deficient, then it's gonna have that. Then or so in the water, when the hydrogen content is high, that means it should have high ferric iron or low. Let me think. I think that should be high, right? It's counterintuitive to me because in figure A you are showing here, then the higher hydrogen concentration in the aqueous in the water, then in order to make the charge balance, then you need to have a higher iron 3 plus, right? So by that, then how could the FeOH plus plus on the left doesn't look right?
Okay, it says although the redox state of the solution might be predicted to control certain stability, once the serpentinizing fluid accumulates enough coupled hydrogen to stabilize ferrous ion species over ferric ion species in solution. So I think they were trying to say more hydrogen can help stabilize ferrous ion.
Okay. More hydrogen, but here on the left, then that's less hydrogen.
Yeah, so it's not ferrous, it's ferric.
Yeah. So that's what I mean. Then they hydrogen will try to stabilize a ferric iron. Is iron 3 plus, right? Think about it.
And then they say the solution redox state no longer adds an important control. Oh, so I was wrong. They wasn't talk about pH thing. They was talking about redox state.
Okay. I think maybe we can understand this way. So when hydrogen is very, very few, then hydrogen H2 doesn't react with iron 3 plus, doesn't react with iron 3 plus because basically it's deficient. So once we put really on the right of the figure A, so push really to the right, then so when log AH2 in aqueous is, for example, -1 or even close to 0, that means in the water there are very, very high concentration of H2. So once you have very high concentration H2, then if there's any iron 3 plus, then iron 3 plus is going to react with H2 to form iron 2 plus and OH bond and OH minus. So that makes sense. Okay. Yeah, because basically on the really right, when log activity of hydrogen is 0, then basically that means H2 concentration is 100%. So in the H2 liquid, there should be no iron 3 plus because there are going to be a reaction to occur. So okay, that makes sense. So when silica deficiency, basically that's on the left. Silica is really deficient, then okay. then the hydrogen could be produced in the water, but the mineral is going to be stabilized. Okay, that makes sense, because we were talking about two things. So on the left is only about the water. On the right is the water and the minerals that are precipitated from that. Okay, yeah, that makes sense. Okay, actually, it's quite a complex chemistry here. Probably it will be very interesting to us in the future once we dig on that. Okay, so could you turn to page 12? So his pity Shichao is not here, because is Shichao here? No. Okay, because I hope he will be on Wednesday, because he has a project that he worked on the different this type of serpentine minerals for classification using machine learning. So probably he has more insights on this. Okay. Okay, yeah, that's another thing. So that how do we know the Precambrian water silicon dioxide concentration? So modern ones I understand, because basically you get all the chemistry right, and then you write the reaction, then you could calculate activity silicon dioxide. But in the Precambrian, how did they do that? So did they use the first one, the reaction they put here, alteration and control hydrogen. Okay, so you have that. So they use this reaction you put here as figure 4, thermodynamic calculation demonstrating the silica limitations on hydrogen production, and they have that. Then the question is that how do they know the serpentine concentration, serpentine composition in Precambrian? Did they tell that about the paper? That
I think they referred to some other papers.
Yeah, well, I'm curious about that. That how did they define the different So I'm thinking about this. If I just look at this reaction they put here, intuitively, I would guess the ocean now is more oxidized than what it used to be, and then we would have higher Fe3 plus serpentine now than what we used to be. So equal to the activity, which is opposite, which is have a negative correlation with the activity of silicon dioxide. Well, high, so now we should be lower. Okay, makes sense. At least qualitatively, it makes sense to me, but I don't know how did they refine that. So Chuntao, do you remember that in Keller and Stoper and Keller 2018 paper, how did they say about this part? Because that's also the serpentinization, like this. I think ophiolite composition they're talking about in terms of the iron 3 plus.
Yes, in Keller's paper, just use the iron 3 plus ratio to talk about the or indicate the oxygen concentration of the seawater, and actually it means that when the oxygen concentration in the seawater is high enough and the iron 3 plus of the basalts erupted onto the seafloor, could be oxidized by the oxygen in the marine or in the seawater, and just use the. But actually, they did not talk about too much about reactions, like the serpentinization of these chemical, these chemical reactions. And I think, but actually it should be low temperature and hydrothermal alteration. I think this process will increase the iron surplus ratio.
Yeah, but I forgot that in the Stoper and the Color 2018 Nature paper, how old did they track samples from the ophiolite? Did they get all the way to Archean? Or is only
Okay.
federal?
Yeah. It does back. I think it does back to 3.8 billion years ago.
Yeah.
I think.
Okay. Wenyu, could you Chunhao, could you share your screen? Maybe we could find that paper to look at it very briefly.
Okay. Please wait. I try to find this paper.
Yeah, because on the right side of the reaction, when we showed in the slide, then that is the iron 3 plus serpentine. There is H2, and it's also silicon dioxide. So we have the 3 parts. So that means on the right, like that, is in equilibrium. Then once you increase any of the 2 components, then you are going to decrease one of them. Okay. I bet if I make a bet, then we would have a lower concentration of ferric iron in serpentine in the early Earth, but I don't know how did they get the hydrogen concentration correct on the Precambrian. If they don't know the hydrogen concentration here in Precambrian, then they could not calculate the activity of silicon dioxide. Yeah, we're going to have a final look, and that figure once Chunhao located. I mean, I could also look it on my end to see if I can find that one.
Yes. Could you see my screen? I'm already.
Yeah.
I
can see the screen.
Yeah, and you could see this record of deep ocean dissolved oxygen from oxidation state of iron in submarine basalt. And actually, this is ophiolites. And we can see in this figure, and this is a iron 3 plus to ratio to total iron. And we could see they have, I think, 3.5 at least. And yes.
Okay. Okay. That's expected. But I don't know how did they get the hydrogen concentration correct in a Precambrian if they want to do the calculation, as what the Tutolo showed before. Okay, but that's okay. I will bear in mind, and then on Wednesday, let's check how he illustrate that, or we can ask a question about it. Okay.
Yes.
Okay.
Actually, yeah.
Okay, that's quite interesting. Okay, on Wednesday, then Ben Tutolo is going to give a talk. Actually, a lot of his project has been on the carbon sequestration, and that they're trying to store carbon in the Earth interior, either by natural process or they're also trying to do that by the industry. So in the oil gas field. So there's a lot of grants for that. Okay, so let's see what it's going to talk about on Wednesday, and that should be pretty interesting. Okay, I think that's so much for today. But before we turn the meeting off, could everybody turn your video on for 20 seconds? Okay, I think that's so much for today. Okay, see you all on Wednesday.